Yeah, let's continue. I shouldn't say continue. We're going to talk about um, optimization or I should say absolute maximum minima. It's not really optimization so much as finding the maximum minima, all that's similar idea. Um, but on a closed boundary. So let's go back a minute. Remember what the date is today, the 23rd. Thank you. So I'll just remind you, back in 17A, we did talk for a minute about how like you could find the critical points or the extrema of a function on a closed interval. An example of that would be finding, say, the absolute maximum and minimum of the function f of x equal to x cubed minus 6x squared on the interval from -1 to 7. And we kind of have to be on a closed interval. Otherwise, a lot of functions don't have an absolute maximum or minimum, right? If you graphed this function, x cubed minus 6x squared, and didn't restrict the domain, your function would look something like this. Sure. And you can see it goes all the way down to -infinity and all the way up to +infinity. So if you didn't restrict the domain here, there is no absolute largest value or absolute smallest value. It's just infinitely large and negatively large. But we're going to restrict the domain to be just from -1 to +7. And then this restricted bit here, or this part of the function that's on the interval from -1 to 7, it certainly looks like somewhere in there there's an absolute maximum. The way I've drawn it, it looks like it's probably over here at x equal to 7, and it has an absolute minimum. And it's either, well, I haven't drawn it very well, it could be here or it could be there. So the way we're going to find where the absolute max and the absolute min is by finding all the critical points, plugging them into the original function, and then also testing the endpoints and plugging those into the original function to see what gives us the biggest value, what gives us the smallest value. We're going to have a similar idea for functions of two variables over regions in R2, in the two-dimensional plane. To finish this problem, I feel like we should finish it. So we would find the critical points in the usual way by setting the derivative, which is 3x squared minus 12x equal to 0. We'd factor. We'd get x times x minus, 3x times x minus 4 equal to 0. So our critical points are x equal to 0 and x equal to 4. Our endpoints are -1 and 7. So to see what thing is the biggest, we're going to plug in f of 0, f of 4, f of -1, and f of 7. So we're plugging into the original function to see what gives us the biggest and what gives us the smallest output. Let's see, f of 0 is going to be, well, our function is x cubed minus 6x squared, or x squared times x minus 6. So f of 0 is going to be 0 squared times 0 minus 6, which is 0. F of 4 is going to be 4 squared times 4 minus 6, which is 16 times -2. F of -1 is going to be -1 squared times -1 minus 6, which is -7. And finally, f of 7 is going to be 7 squared times 7 minus 6, which is 49. So we can see our absolute biggest value is 49, and our absolute minimum value is -32. Couple things about language / notation here. In this example, I would say the absolute minimum occurs at x equal to 4 with a value of f of 4 equal to -32. Similarly, I would say the absolute maximum is at x equal to 7 with a maximum value of f of 7 equal to 49. So it's always occurring at the input with a value of whatever the output is. Yeah, so we're just gonna do this now for some functions of two variables, but there's a few kind of things to see here. So let me actually do one thing real quick here. Just want to remind myself of one example that I have set up. Oh, I know what that example is. Never mind. So yeah, let me draw these pictures. Sure. So let's say we have the following situation. We want to find the absolute minimum and maximum values. So when they say find the maximum or minimum values, they are asking for the outputs. Usually we say everything though. On the closed boundary, which is given by D equal to the set of all points x comma y, such that x is between -1 and 1, and y is also between -1 and 1. But look how I've written it in different ways. Here I wrote x is between -1 and 1. Here I wrote the absolute value of y is less than or equal to 1. Those mean essentially the same thing. So we're just within a square that has corners at 1, 1, 1, -1, -1, -1, and -1, 1. Find the absolute maximum of values on the closed boundary of the function f of x, y equal to x squared plus y squared plus x squared y plus 4. So the idea is similar to what we did before, but not exactly the same. We're still going to find critical points. We're still going to test quote unquote endpoints, but the endpoints are now going to be the corners of our region. And then we're also going to have to do this thing where we figure out what's going on what I like to call either the boundaries or the walls. So let's draw the picture of our region D. So here's our XY axis. And all we're doing is saying that our x's are between -1 and 1, and our y's are between -1 and 1. So our region looks like this. It's a 2 by 2 square. And this boundary up here is y equal to 1. This boundary over here is x equal to 1. This is y equal to -1. This is x equal to -1. So this next part I'm not great at drawing the pictures for. So I'm just going to show them to you instead because I think they're worthwhile. So the thing is, we've got some surface above this region. And we're trying to figure out where on the surface the highest point is and where on the surface the lowest point is. And there's three kind of categories of where that highest point or lowest point could occur. So let me show you this picture that Grant has drawn for us, which looks so lovely. So here's one thing that could happen. Maybe you have like kind of a typical looking roof. I'm thinking of this really as like the floor of your house, and then here's your house, here's the walls, and then here's the roof. And we're trying to see where is the roof the highest, where is the roof the lowest. So one option is the roof is the highest somewhere in the middle. So there's some critical point in our region that's going to give you a maximum value. And then our minimums are like, well, basically the whole edge border is the minimum, which is not really going to happen, but it could. Another option, though, is that your roof looks something like that, where it's kind of slanted up towards one corner. So the highest point, the maximum, is occurring at one corner, and the minimum is occurring at some other corner. That's totally possible, especially if the function you are looking at is like a plane equation. Like if your function f of xy was like 2x plus 3y plus 0, or plus 1, whatever, that would be something that just slanted upwards in one direction, and your maximum is going to be at some corner, and your minimum is going to be at some other corner. Those two feel pretty easy to understand. The third thing that can happen, though, is kind of the weirdest one, which is something like this next picture, where your roof does something like this. So on some boundary, you have a maximum like that. So we have to test not only all the actual critical points and all the corners, but any pseudo-critical point that ends up on one of the 4 or however many boundaries there are. Usually your regions will be rectangles, but they don't have to be rectangles. So we're going to check every boundary, and then we're going to see if we can find any critical points along that boundary. All right, let's do it. So, actually, I should ask, are there any questions about the pictures or like what I'm saying? I think it's not too hard to see what's going on there, but doing it, I think, helps a lot more. And then we'll look at some graphs. Yeah, so let's look at this example first. So first step, find the critical points. So in the usual way, we're going to find critical points by taking each partial derivative, setting it equal to 0, and doing the thing. So my fx is going to be 2x plus 2x times y, set that equal to 0. My fy is going to be 2y plus x squared equal to 0. I'm going to deal with the first one because it looks like from the first one I can factor out the 2x. So if I do that, I'm going to have 2x times 1 plus y equal to 0. So half of a critical point is either going to be x equal to 0 or y equal to -1. But those don't go together, right? We're going to take the x equal to 0, plug it into the other equation. If x equals 0, then we're going to get 2y equal to 0, which means y equals 0. So if x is 0, our critical point is 0, 0. And if y equals -1, we plug that in there. We get -2 plus x squared equals 0. We get x squared equal to +2. We get x equal to the square root of 2. I should say plus or minus the square root of 2. So our critical points here are +√2, comma, -1, and -√2, comma, -1. Let me check something. Let's see one thing. Sure, yeah. So now we're going to do a couple things. First of all, I like to draw my critical points in my region. I find it helpful. So if I start drawing them, let's see, I've got 0, 0, which is right in the middle. And then I've got x is +√2, which is bigger than 1. So one of my critical points is out here. It's still a critical point, but it's not one I care about in this problem. The only points we're concerned about are the points in the interval or in the region. So these two critical points, these are outside of the region, so forget about them. We don't care about them. Now, if this problem had a different region, like if y and x and y were both between, like, say, -2 and +2, then these two critical points would definitely be inside of our region. So we have to be in the region to care about them. The next thing we're going to do, and this is kind of the harder part, is we're going to look at all the boundary critical points. So here's what I mean. Yeah, we're going to look at each of the boundaries, or as my coworker Grant likes to call them, the walls of your house. So let's look at, say, the wall x equal to 1. So I want to point something out. If x equals 1, x isn't changing. X is always 1. So to find any critical point, you're just going to take the partial derivative after you set x equal to 1 with respect to y. So if we plug in x equal to 1, our new equation, our new function, f of 1 comma y, I'm plugging in 1 for x, is going to equal 1 squared plus y squared plus 1 squared times y plus 4. And if I take the partial derivative of that, fy is going to equal 2y plus 1. We set that equal to 0. We get y equal to -1/2. So a critical point along that wall is going to be the point 1 comma -1/2, which is living about right here. We're going to do the same thing for every boundary. So for the next one, we're going to set x equal to -1, and we're probably going to get the same results. What do I mean by that? Well, actually, we might not get exactly the same result. I take it back. Let's set x equal to -1 and see before I start saying things that might not be true. So if we set x equal to -1, our f of -1 comma y is going to be -1 squared is still 1. Y squared is still y squared. X -1 squared is still +1, so I get 1 times y plus 4. And if I take the partial derivative, it's going to be exactly the same as it was up here. My fy is going to be 2y plus 1. If I set that equal to 0, I'm going to get y equal to -1/2. But I also have a boundary critical point at -1 comma -1/2. So up over here. We do the same thing with the y's. So now we're going to set y equal to 1 because that's another boundary. Set y equal to 1. Now our equation becomes f of x comma 1 equal to x squared plus 1 squared plus x squared times 1 plus 4. We take the partial derivative with respect to x now. It's going to be 2x plus 2x, which is 4x. Set that equal to 0. We're going to get x equal to 0. So we have a critical point at, I should say a boundary critical point at 0, 1. Looking up here. And finally, our last boundary, we set y equal to -1. We're going to get f of x comma -1 is equal to, let's see, plugging it in again, we're going to have x squared, still plus 1, plus x squared times -1, plus 4. And if we simplify that, the x squared is going to be canceling, and we get f of x comma -1 is equal to 5. Yeah, 5, that's a 4 over there. Sorry, that's a 4. So here's what's happening here. Along this boundary, the function is just always equal to 5. So it's basically just a flat line or a flat boundary end. So it's not going to have a max or a min on that. Or if all of them were maxes or mins, we would just find them at the endpoints. So typically when this happens, if you take the partial derivative and set it equal to 0, well, it's already 0. So we're not really finding any critical points. Or I guess the better way to say it is every point on that boundary is a critical point, but really we just kind of ignore it. So we're not going to worry about this. But if that wall of the house is all minimum or maximum, then we'll say all the points between, say, like where y equals -1, where we go from -1 to 1 -1, and be every point on that board. But that doesn't usually happen, so I wouldn't worry too much about it. All right, so now we're going to test all the critical points we found, along with all of the corners. So we got a lot of things to check. 1, 2, 3, 4, 5, 6, 7, 8 things. All right, so we're going to plug all those points into the original function. So here we go. Maybe let's write down the function again. So our function is, once again, f of x comma y is x squared plus y squared plus x squared y plus 4. And then we're just going to start plugging in each of these critical points. So f of 0 comma 0 is 0 plus 0 plus 0 plus 4. F of 0 comma 1 is 0 plus 1 plus 0 plus 4. F of, sure, there's lots of points here. F of -1 comma 1/2 is going to be a little bit dicier. That's going to be -1 squared plus 1/2 squared plus -1 squared times 1/2 is 1/2 plus 4. We add that all together, we get 5 plus 3/4, so we get 5 3/4 or 5.75. We keep going, right? This part is the part that's terrible, right? You just have to plug it in every function, but there's really no other way around it. So now we're going to plug in +1 comma. Oh, you know what? I made a tiny mistake here. That should have been a -1/2 I was plugging in for y. Sorry about that. So that should have been 1, still plus 1/4, but then it would have actually been a -1/2. So instead of getting 5.75, we should have gotten 5 minus 1/4, which is going to be 4.75. Sorry about that. And then for the 1 comma -1/2, I think we're going to get the same thing. We're going to get 1 squared plus -1/2 squared is still 1/4. And 1 squared times -1/2 is -1/2 plus 4. That's also equal to 4.75. We keep going. Okay, so that's my original critical point. These are my 3 boundary critical points, and the rest of them are just the corners. So we're going to find f of 1 comma 1, which is 1 plus 1 plus 1 plus 4. F of -1, 1, which is going to be 1 plus 1 plus 1 plus 4. F of 1 -1, which is going to be 1 plus 1 minus 1 plus 4. And f of -1, -1, which will also be 5, because it's going to be 1 plus 1 minus 1 plus 4. All right, we did it. So now we just have to figure out which ones are the biggest. So let's see. These two look like the biggest. And where's the smallest? It looks like the smallest is 4. So we would say, so there's a couple ways we can answer this question, depending on how it's asked. The way it was phrased is just asking for the maximum minimum value. So we could say, cool, our absolute maximum is 7. our absolute minimum is 4. But a more kind of, what's the word I'm looking for? A more complete answer would be to say we have an absolute minimum of f of 0, 0 equal to 4. Because writing it that way tells you not only what the value is, but where it occurs at, which I think is a better way to answer the question. And then we have multiple absolute maxima. We have absolute maxima, plural, of f of 1, 1 equal to 7, and f of negative 1, 1 equal to 7. Yeah, gross. Questions about any of that before we do another one where I'll get to show you a cool graph as well. Most of the time they're squares. Or I would say more broadly, most of the time they're rectangles, because maybe the x length and the y length will be different. But I think I was just looking at the problems in the textbook earlier. Where did I hide you from myself? There we go. The problems in the textbook are problems like 17 through 20. No, or I don't remember. I don't know if all of them were assigned that, but certainly 17 and 18 are triangles. 19 and 20. 19 is a square. 20 is 19 is the square we just did. 20 is a rectangle. So those are the most typical shapes we usually encounter because they're relatively easy to find what's happening on the boundaries. Let's look at another example that we're more familiar with though. Yeah. Is that the example? Let me sorry. I need to double check one thing just so that I don't show you the crazy example I'm thinking of. I want to show you the cool example I'm thinking of. So one moment while I look something up in my Desmos 3D graphs. Let me just see here. So I'll make sure I don't give you the wacky one. Where'd you go? To you? Yeah, it is you. Oh no, it's not. It's the one we just did. Cool. So let me show you the graph of that instead. Apologies. So I will point out there is one thing about my graph that is different. No, it's exactly the same. Never mind. So let me just show you this. So here is the actual surface that we just graphed, but limited to just the negative one, the 2x2 square. You can kind of see that if we flip things around, right? It's a square, but the surface looks like that. And so you can see over here at that point right there, can I click on it? That's the point 117. Oh yeah, that's clearly the highest that thing goes. It'd be kind of a weird roof to build on your house, right? This thing that would catch a lot of rain. You'd probably want to flip it over and have it the other way. But you have a maximum there and a maximum there at both with values of 7 and inputs of 1, 1 and negative 1, 1, just like we said. And then our minimum is down here at the origin, right? At the bottom there is a minimum sitting at 0, 0, 4. I will also point out though, and I think, this is kind of interesting, on our boundaries, right, we do have on this, say like, right, on this x equals 1 boundary at where y equals negative 1/2, this is kind of hard to see there. No, that's too much, James. Sorry. That blue point right there, that is a minimum along that boundary. It's not an absolute minimum, but that point there certainly is the lowest thing on the boundary x equal to 1. So hopefully this kind of helps you see the idea of what's happening, why we're testing all the things, right? Because the corner could give you a max or a min, or a real critical point in the middle could give you a max or a min, or it could have been possible that this point on the boundary could have been your maximum or minimum. Kind of neat. I do think it's kind of neat. That said, we'll do maybe 1 or 2 more examples. Let's do one with a triangle. I think the triangle ones are kind of neat. They have a little extra flavor to them. Oh, and here's the attendance form, if I forget. Where's my triangle example over here? Let me make sure this isn't the same triangle as the one that's already in the textbook. Not that would be terrible, just. Nope, it is the exact same one in the textbook. Okay. Let me grab a different example then. Where'd you go here? Let's see. One moment. Do I have? Oh, that should be fine. Yeah. Cool. Let's look at this example. So often when we do an example like this where the region is triangular, they just kind of describe where the vertices are. So we want to find the absolute maximum and minimum, or we could just say absolute extrema of the function f of x comma y equal to 3 plus xy minus x minus 2y on the triangular region. Let me check one thing here. Sure, yeah. With vertices 0, 0, 0, 5, and 5, comma 0. And it's not absolutely necessary, but I do think it's a good idea to draw the region. I would always draw the region, or I guess the domain, you might also call it. Here's my triangle with vertices 0, 0, 5, 0, 0, comma 5. So we're going to find all the same three types of critical points. So first off, we know we're going to be testing 0, 0, 5, 0, and 0, 5, right? Automatically, for sure, we always include the endpoints. And then we're also going to look for any regular critical points. So to find our regular critical points, we're just going to take the partial derivatives, set them both equal to 0. Fx is going to be y minus 1 equal to 0, only gives us y equal to 1. So there's half a critical point. Fy is going to be x minus 2 equal to 0. So we have to get the other half of our critical point is x equal to 2. So our critical point is 2, comma 1. So that is in our region, right? If you go over 2 and up 1, it's about right there. You don't have to draw anything. You just have to make sure that you know that that critical point either is or is not inside the region. It's also fine for it to be on the border, but it can't be outside of the region. Okay, so now we find the walls. So two of the walls are really easy. This bottom wall is just the equation y equals 0. This left wall is just the equation x equals 0. So for y equals 0, we're just going to replace each y with 0. So look at this. We get f of x comma 0 equal to 3 plus 0 minus x minus 0. So that's going to equal 3 minus x. If we take the derivative of that, our derivative is -1. What does that mean? Well, along that wall, we're essentially saying the slope is always -1. So whichever way we're going, right, if our wall is starting here and ending here, we're essentially just going down that way. So you definitely can't have a max or a min along the wall because you essentially just have like a straight line that's either increasing or decreasing. In this case, decreasing. So that means we're just going to be left with the endpoints. And I think the same thing's going to happen along the other easy wall. We plug in x equal to 0. We get f of 0 comma y equal to 3 plus 0 minus 0 minus 2y. And we take the partial derivative of that. It's going to be -2. And again, -2 doesn't ever equal 0. Just like -1 doesn't ever equal 0. So these two walls don't give us any new critical points. But the third wall, which is this line here, now that line should be relatively easy to find the equation of. If we start at 0, 5, and we also go through the point 5, 0, what's the slope of this line? It is negative, but negative how much? Yeah, it's -1. Right, we've gone over 5 and down 5. Oh yeah, -5 over 5 is -1. So our slope is -1, and our y-intercept is +5. So the wall we're plugging in is y equal to -x plus 5. So check it out. Our equation f of xy is going to become f of x comma -x plus 5. We're going to replace each y with -x plus 5. So that's actually a little more interesting. When we do this, we're going to get that equal to 3 plus x times y, which is -x plus 5, minus x minus 2 times -x plus 5. Should left myself a little bit more room here. If I simplify this, it's going to be 3 minus x squared plus 5x minus x plus 2x minus 10. And if I take the derivative over here, sorry about that, my partial derivative with respect to x is going to be negative 2x plus 5. I could have probably simplified this more. Plus 5 minus 1 plus 2, which becomes negative 2x, let's see, plus 6 equal to 0. So we end up getting x equal to 3. And if x is 3, the y value is negative 1 times 3 plus 5. So negative 3 plus 5 is y equal to 2. So our other critical point, our boundary critical point is 3 comma 2, and it should be on the boundary. So that's kind of weird when it works out that way, but that's always going to happen with a triangle. For a triangle, at least one of your boundaries isn't just going to be a y equals something or an x equals something. One of them has to have some sort of slope to it that is not just 0 or undefined. All right, we have all the points. How many critical points do we have to test here? How many? Show me on your fingers. How many critical points do we have? Yeah, we have 5. 3 corners and the 2 red ones we just found. So we're going to plug all those into the original function once again. So let's see here. Sure, we can do that. So let's see. F of 0, 0 is going to be 3 plus 0 minus 0 minus 0. F of, let's do the corners first, sure. 5 comma 0 is going to be 3 plus 5 times 0 is 0, minus 5 minus 0. So 3 minus 5 is negative 2. F of 0 comma 5 is going to be 3 plus 0 minus 0 minus 10. 3 minus 10 is negative 7. And then my critical points, F of 2 comma 1 is going to be, let's see, 3 plus 2 times 1 minus 2 minus 2 times 1, which is going to be 1. And finally, the last one, F of 3 comma 2 is going to be 3 plus 3 times 2 minus 3 minus 2 times 2. And that's going to be 9 minus 7, which is 2. So it looks like our absolute maximum is over here at 0, 0. And our absolute minimum is over here at negative 7. So absolute maximum of f of 0, 0 equal to 3. Absolute minimum of f of 0 comma 5 equal to negative 7. I would say the way I'm writing the answer here, I think this is the most succinct way of writing the answer. You're including all the information you can with as little writing as possible. Trying to knock things over here. Sure. So how I found the equation or how I plugged it in? Right. Yeah. Sure. And yeah, and I know it's kind of cramped in here. So what I did was, so I took my original equation, f of x comma y equal to 3 plus xy minus x minus 2y, and I replaced y with what it was equal to, which is negative x plus 5. And then I plugged it in and I got 3 plus x times negative x plus 5 minus x minus 2 times negative x plus 5. Well, because that's the equation of this line, right? So that boundary, right? That boundary is the line y equals negative x plus 5. So if a point is on that boundary, it has to satisfy that equation. So we're saying, cool, we're just going to replace y with what we know it has to be equal to. So then if we do this, right? So what I should have done to be a little bit more careful about this is I should have simplified this more nicely. This is 3 minus x squared plus 5x minus x plus 2x minus 10. And if I simplified that more, I would have had minus x squared, 5x minus x is 4x plus 2x is 6x, 3 minus 10 is negative 7. And then I would take the partial derivative and get fx equal to negative 2x plus 6, set that equal to 0, get x equal to 3. However, you could have also said, I don't want to write my equation in terms of x, I want to write it in terms of y. So you could have taken the equation y equals negative x plus 5 and solve for x instead. It's actually kind of the same equation. You get x equal to negative y plus 5. And you could have done it that way. You could have said, cool, my f of negative y plus 5 comma y. Now I'm going to replace every x with what it's equal to. That's going to be 3 plus negative y plus 5 times y minus negative y plus 5 minus 2y. Simplify. 3 minus y squared plus 5y plus y minus 5 minus 2y. Simplify more, you get negative y squared plus 5y plus y is 6y minus 2y is plus 4y. And then 3 minus 5 is negative 2. If we take the partial derivative of that, we get negative 2y plus 4 equal to 0, which is going to give us that y is equal to positive 2. Which if you then plug back into this equation, will give you x equal to positive 3. So either way you do it, you should still get the same critical point on the boundary. You're just going to find the y coordinate first or the x coordinate first. Yeah. Yeah. There's not a whole lot more to say about that. Oh, sure, yeah. I had one other thing in mind though. Yeah, we got time. We have enough time. So let me give you one more optimization problem, if I can find it. -7 is the absolute minimum. Yes. Yeah. Sorry, just a little wishy-washy about what we should do for this next problem here. Sure. Let's do one more. More optimization. It's always good to practice optimization because it feels like it's a new thing every time. So here is an example. I'm always partial to these examples. A manufacturer wants to construct boxes without lids. I don't know why he would want lids, but whatever. It's what he wants. That hold 32 cubic feet of volume. What dimensions of the boxes will minimize the amount of materials used? So usual setup, we have a thing we want to minimize or maximize and a constraint. I'm going to draw a picture. There's my box without the top. I don't know any of the dimensions, so I'm going to say they're X, Y, and Z, which is typical. Our thing we want to minimize. So when they say minimize the amount of material that's used, they really mean minimize what? The surface area, right? That's the amount of material used, the amount of cardboard or whatever you're making your box out of. So we want to minimize the surface area, which is equal to the bottom rectangle, which is X times Y, plus the front and back rectangles, which are both X times Z, plus the left and right rectangles, which are both Y times Z. And now our constraint is that the volume should equal, well, the volume is X times Y times Z, and it should equal 32. And the rest of this is pretty much the same thing we've done a few times, but right, we isolate a variable, we plug it into the other thing. Oh, I should stop for a moment. Nope, I'll just check it. I'm going to check it in again. You guys should tell me. No one's talked about Lagrange multipliers, right? You haven't heard the words Lagrange multiplier or talked about lambda in any sort of way? Cool. If you do, please let me know and we will talk about it. But I think I'm getting the impression that both of your professors are going to skip it, but that could be not true. So let me know if you talk about Lagrange multipliers. It is kind of a nicer way to solve these things sometimes. When, who knows? So z is equal to 32 divided by xy or multiplied by x inverse y inverse. So then if we plug that into this equation up here, our surface area equation now is going to be x times y plus 2 times x times 32 x inverse y inverse plus 2 times y times 32 x inverse y inverse. It is always a good idea, always, to simplify this thing before we start taking partial derivatives. It's going to equal xy plus 2 times 32 is 64. The x's cancel and you get y to the negative 1. Same deal over here. You get 64 x to the negative 1. Now we take the partial derivatives. So our surface area partial derivative with respect to x is going to be y minus 64x to the negative second. And the other partial derivative with respect to y is going to be the same thing, except with x equal minus 64y to the negative second. And these ones always feel funky. I feel like last time we solved this one, I did the thing like, so I would probably think of writing this as y equals 64 over x squared. And this one as x equals 64 over y squared. And plugging in y equal to that in there is what we should do, but it just feels like not the best. But I don't really think there's a better way of doing it. I wish there was a better way of doing it, is what I'm really trying to say. But no, I'm not seeing it. So yeah, we do it. Actually, okay, I see one thing we could do. We could instead write this as y times x squared equal to 64, and then plug in x there. It kind of feels a little bit better than having a fraction squared in the denominator of some other fraction. So if we plug this in for x there, we have y times 64 over y squared squared equal to 64. This isn't so bad. Nicely, kind of greatly here, I don't actually need to know what 64 squared is, even though we could figure it out. But here's what I mean. If we rewrite this, we have y times 64 squared over y squared squared equal to 64. We cancel a y here, multiply both sides by y cubed, and have 64 squared equal to 64 times y cubed, and then divide both sides by 64. So you have 64 divided by 64, 64 squared divided by 64 equal to y cubed. So sometimes you can avoid doing the terrible multiplication if you just notice something. Oh yeah, I have a 64 over there. It's going to end up canceling one of the 64s. And then we get y equal to 4. We plug back in that x is equal to 64 over y squared, which is 64 over 16. I feel like we did this problem before. We might have done this problem already. Oh well, sometimes it's good to see the same problem again. And then finally, z is going to equal 32 divided by x times y, which is 32 divided by 4 times 4, which is 2. So our dimensions are 4 feet by 4 feet by 2 feet. How do we know this is a maximum? No, a minimum, right? Which one is it? How do we know it's the thing we're trying to get? Well, we probably need to find D and do the whole thing. So here's our first partials. So our D which is going to be the second partial with respect to x, the second partial with respect to y, minus the mixed partial squared. Yeesh. All right, so it's not as bad as it looks. Our second partial with respect to x is going to be positive 128 times x to the negative third. And for y, it's going to be positive 128 times y to the negative third. And for the mixed partial, it's going to be 1. So if we plug in our point, which is x equal to 4 and y equal to 4, we're going to get 128 divided by 4 cubed, and the 128 divided by 4 cubed minus 1 squared, and that's definitely going to be positive. Because 128 over 64 is 2, equal to 2 times 2 minus 1, which is 3. And you have to do one more thing. You have to say, oh yeah, it's positive, means you could have a max or a min But then we look at fxx, or I should say saxx, which is positive, which means it's concave up, which means we have a minimum. So yes, we have a minimum surface area as desired. And let's call it a day there. So for those of you in Varn's class, or I mean anyone's all going, but here's a practice exam, grab a copy of it. And I'll post solutions to that today or tomorrow, depending on how much time I have today. And I guess I'll see you on Friday before your exam, for those of you that have it, right? Your exam's in the afternoon. So if you have burning questions on Friday about possible exam stuff, you're welcome to ask them. Otherwise, we'll probably start talking about double integration. I believe that's where we go next, briefly, which is not in the textbook. It's always like extra material to be like, you should learn this. So here it is. It's not in the textbook.